So we're going to take a look at using vectors to solve some problems. Oh yeah. So in example number 1, we're to write this vector in component form. Now, vector in component form, you have these brackets here. This is telling us we're talking about a vector and its components. And its components are based on its x and y changes. So you notice we have an arrow here at point H, which means we're going in that direction. We're going from G to H. So from G to H, we are going to go over 1, 2, 3, 4. And that's a movement of 4 in the positive direction. And we're going down 1, 2, 3, 4, 5, 6. So that's a movement 6 in the negative direction. And that's all component form is. Now, for example 2, we're to draw the vector and find the magnitude to the nearest 10th. So it doesn't matter where I place the vector on the grid, I just have to go left 1 and up 5. So I'm going to call this point here A. It's a huge point, right? And I'm going left 1, that's 1 in the negative direction in x, and 5 up. 1, 3, 4, 5. And so there's my vector right here. And now I need to find the distance. Now, to find the distance, I'm just simply going to use the Pythagorean Theorem. So I'm ending up with this triangle that has these side lengths. So we have 1 squared plus 5 squared, which is equal to c squared. So 1 squared is 1, 5 squared is 25. So we end up with 26 is equal to c squared. And then you take the square root, and so we get c is equal to the square root of 26. Now 26 doesn't have any perfect squares, so obviously this is asking for a calculator, but I'm going to leave it in its simplest radical form right now. All right, so example number 3. The force of a sphere is given by the vector 1, 4. Draw the vector and find the direction to the nearest degree. All right, so this one's a little trickier. So we have a vector that's going 1 over and 4 up. So 1 over, 4 up. 1, 2, 3, 4. Okay, my calibration is a little bit off on the board, which is making it a little bit difficult to have this work out. All right, and so here's the thing. I know this is due north, right? And so what I need to do is I need to find this angle here. And so if I set up a right triangle, I have a side length of 1 and a side length here of 4. And so I need to find this angle here. And well, the tangent of this angle, of angle theta, is equal to, and tangent is the opposite over the adjacent. So the opposite side in this case is 1, the adjacent side in this case is 4. So I need to know what angle has a tangent of 1/4. So I'm going to go to my calculator. Oh, really, I'm going to go to my email. And I need a scientific calculator. All right, so I need an inverse button here, and this is definitely in degrees. All right, and I don't have an inverse button. That's really helpful. Not helpful. Oh, maybe this. Yep, there we go. Okay, so we do have it. All right, so I need to know inverse tangent. So let's try this again. So we're going to do inverse tangent of 0.25. And so it has an angle of 14 degrees, roughly. All right, so now I still need to talk about the direction, right? So this means that I'm heading north But I'm going not due north, I'm going north with a, with a 14-degree east angle. So I'm going north and then 14 degrees to the east. So that's how I'm going to go ahead and show this answer here. Now for the most interesting problem. An airplane is flying at a constant speed of 400 miles per hour at a bearing of north 70 degrees east. A 60-mile-an-hour wind is blowing due north. What is the plane's actual direction and actual speed and direction? Gotta love it when I find typos while I'm recording. All right, so here we go. So if this is due north, I'm gonna have a vector line that is, and this is east, right? I have an airplane that is going at 400 miles per hour. So this is 400 miles per hour. And I know that this angle here is 70 degrees, which means this angle here is 30 degrees. So this vector that I've drawn is north 70 degrees east. And I'm specifying that that length, the magnitude, is 400 miles per hour. And we're adding to this a wind that is going due north at 60 miles an hour, which means our resulting vector, using the tip-to-tail method, is right here. It's the sum of these two vectors. So now I need to find this magnitude as well as the angle that we have there. Now, to do this, it's going to require some rules of trig. So, what do I know about the rules of trig? Well, I know that the law of sines is going to be your the sine of an angle over the side, and that's going to equal the same for all of them, all the ratios of the side length and the angles. And the law of cosines is going to say that, well, let's say we have a squared is equal to b squared plus c squared minus bc, 2bc, times the cosine of a. All right, so we have these two tools to work with. So the question becomes, what do I know? Well, I have two side lengths. I'm trying to find the third. Well, do I have any angles that I can work with? And so, well, let's see. How can I go about doing this? And I also know that I can I can add vectors using component form as well. So obviously, the component form for this first vector, or sorry, for the wind vector, I have 0, 60, because it is not moving left or right, it is moving straight up at 60 miles an hour. Well, which means, well, I need to turn this vector right here into component form as well. So to do that, I'm going to turn this into a right triangle. All right, well, I need to find this component and this component. So if I know this angle right here is 30 degrees, that means that for the horizontal component, the cosine of 30 has to equal something, x. I'm going to call this x, by the way, over 400. So I'm going to go back to my calculator here. I'm going to do the cosine of 30 times 400. Now I'll get my x component. So here we go. Clear that out. So we go 30, and we want the cosine. Oh, geez. Clear it. One of these days I'll learn how to use the computer. So 400 times the cosine of 30. And so that means that component is 346.4. Go over here, through 346.4. And then for my vertical component, my due north component, I'm going to do the sine. I'm going to do 400 times the sine of 30. So I'm going to go back to my calculator. So we have 400, that's 4,000, times the sine of 30. I get 200, all right? Oh yeah, because the sine of 30 is 1/2, isn't it? 200, half of 400 is 200. So we have this as 200. Which means the resulting vector is going to be, I'm just adding these together. So 0 plus 346.4 is 346.4. Then add those, we get 260. And so now I can use the Pythagorean theorem to find my magnitude. So I'm going to square 346.4, I'm going to square 26, and then take the square root, I'll get my magnitude. So 346.4, and then I'm going to multiply it by itself, 346.4. All right, that is a fairly large number. I'm going to write that one down so I don't forget it. 11992.96.
Still recording?
I am still recording.
Okay.
And then we have 260 times 260, and that is 67,600. And I'm going to add that to 11992.96, and then I'm going to take the square root of it. So 187,592.96. Hit enter, and so we know the airplane is actually traveling 433 miles per hour. So going over here, we have an actual magnitude of 433. All right, so now we have all the side lengths. The next thing we need to do is we need to find this angle here, or we know that using vector addition, this side is 260. So now, and we know that this is 433. We can, wait a second, we also know that this is 346.4. I can use either or any of my trig functions to find the resulting angle here. So let's go ahead and do that. So I'm going to use, opposite, so I'm going to do adjacent over hypotenuse, which is cosine, opposite, so we're using cosine here, so we're going to do it's a joke. So we're going to say that the cosine of angle theta is equal to, so it's the adjacent over the hypotenuse, so we have 260 over 434. So I'm going to go back to my calculator. And so we have, forgotten what I was writing. We have 260. So we have the inverse of cosine, and we have 260 divided by 433. Hit enter. So we have a 53-degree angle, which means that the vector is going north 53 degrees east at a magnitude of 430 meters. All right, there you go.